Welcome to the sixth session of Basics of Remote Sensing. Here we will discuss about different types of errors and corrections in remote sensing, which covers concepts on errors in raster data, types of error, how these errors occur, and how to correct these errors. Myself, Anup VM, Senior Geologist, Photogeology and Remote Sensing Division, Geological Survey of India Training Institute, Hyderabad. Image quality. Most of the remote sensing data contain very high quality accurate data. But unfortunately, sometimes error in the form of noise will be introduced into remote sensing data by the effect of environment like atmospheric scattering, the presence of clouds, etc. These random or systematic malfunctioning of remote sensing system is also a reason for affecting the image quality. That may be due to the uncalibrated detector, which may create strippings, or it may be due to improper pre-processing of the remote sensing data prior to actual data analysis. Let's see about errors in a raster data. The noise in a data refers to deviation of digital number from its original value. There are different sources of errors, can be classified as internal and external. Internal errors are otherwise called as systematic errors or sensor driven errors, which are applied to all images from the particular platform. External errors are otherwise called as non systematic errors that may be due to perturbations in platform or atmospheric scene characteristics, which is applicable to an individual. Geometric errors. All remote sensing images are subject to some form of geometric distortions, depending on the manner in which the data are acquired. These errors may be due to variety of factors. Systematic errors. These errors are system dependent and also called platform based errors, mostly found in mechanical sensors. That may be due to scan skew in the form of mirror scan velocity variance, as a panoramic distortion, as a platform velocity difference, and due to the difference in earth rotation and data acquisition. Due to the earth rotation difference, earth rotates as the sensor scans the terrain. This results in a shift of the ground swath being scanned. Hope you remember what is a swath, which we discussed in our earlier class. This causes along scan distortions for the image. Satellites which are having small swath width have less earth rotation effects. The interaction between the fixed orbital path of the remote sensing system, that is north to south or south to north, and the earth rotation, that is from west to east on its axis, skew the geometry of the imageries collected. In this picture, you can see that difference regarding a Landsat satellite line of flight and the shift in the scan lines. Scan skew. During the time the scan mirror completes one active scan, the satellite moves along the ground track. Therefore, scanning is not at right angles to the satellite velocity vector, that is the ground track, but it is forming as a slightly skewed form, which produce along track geometric distortion. In the below figure, we can see the direction of the earth rotation and the distortion which is created due to the earth rotation. Non-systematic distortion. Non-systematic errors are mainly caused by variation through time in the position and attitude angles. Altitude. If the sensor platform departs from its normal altitude or the terrain increases in the elevation, this produces change in scale. Here we can see the altitude variation with the original data as well as if an altitude variation is occurring. Attitude. One sensor system axis is usually maintained normal to the Earth's surface and the other parallel to the spacecraft's direction of the travel. If The sensor departs from this attitude, geometric distortions results. As explained in the previous slide, the geometric distortion depends on not only the geometry of the sensor but also the attitude of the platform. Therefore, it is very important to measure the attitude of the platform for consequent geometric corrections. What are the attitudes of the platform? It can be classified into different rotation angles around three axes, as you are seeing in this picture: lateral axis, longitudinal axis, as well as vertical axis. We call them as pitch, yaw, and roll. The rotation angles of roll, pitch, and yaw are defined as the rotation angles around the flight direction, the main wing, and the vertical lines, respectively. If any changes happening for this axis, there will be a distortion in our imagery. It has been shown in the picture below. You can see during the aircraft movement, the changes happening to these lateral axis, vertical axis, as well as for the roll, how it is changing. So due to the above mentioned errors, there will be displacement on our satellite imagery. You can see over here as a forward and afterward tilt, sideward tilt, as well as a rotational change to the satellite imagery. Now we will discuss about radiometric errors. Radiometric errors and inconsistencies are referred to as noise, which could be considered any undesirable spatial or temporal variations in image brightness. It may be due to system errors and non-system errors. System errors are in the form of line dropout, which is caused by a defective sensor in the system. There are line strippings, which are caused by different responses of detectors to equal input, that is due to decalibration of detectors. Banding. These are caused by variation of neighboring forward and backward scans. This is visible in Landsat thematic mapper products. Random noise or spike are other systematic errors caused by error during data transmission or due to some temporary disturbances. There are non-system errors or atmospheric errors due to the scattering and absorption characters in the atmosphere or due to the topographic attenuations. Here we can see line banding and stripping errors in Landsat 5TM, Landsat 7 ETM data, as well as a temporary occurred during 2019 December in Landsat 8 data. I have few questions for you. Question number 1. Geometric distortion of attitude and altitude is a options. Option number 1, systematic error. Option number 2, non-systematic error. What is the answer? Non-systematic error. Question number 2, line stripping is a options. Option number 1, radiometric error. Option number 2, geometric error. What is the answer? Answer is radiometric error. Now let us discuss about corrections of remote sensing data. First is geometry correction. As a pre-processing of satellite imagery or data, we do corrections, geometry corrections. In order to remove geometric distortions and so that individual picture elements or pixels fit into their proper planimetric map locations. We are doing geometry corrections so that corrected imagery can be used to extract accurate distance, planimetric map locations. We are doing geometry corrections so that Corrected imagery can be used to extract accurate distance, polygon, area, and direction information from a data. We can overlay the image data with other thematic layers. In order to understand a sequential change detection studies about an area can be accurately done if you are doing a geometry correction. In order to derive a two-dimensional or three-dimensional coordinates, we are doing geometry corrections. We can visualize an image data in a GIS environment. Also, we can merge an image data of different spatial resolutions. While mosaicing an image, it should have a proper geometry corrected data. We can overlay various vector data as a shapefile on an image. Few components related with geometry corrections. Ground control points. What is a ground control point? A ground control point or GCP is a location on the surface identified on the imagery and located accurately on a map. As an image analyst, we must be able to obtain two distinct sets of coordinates associated with each GCP. That is, image coordinates specified in I rows and j columns, and map coordinates, for example, xy measured in degrees of latitude and longitude, or meters if it is in a UTM projection. The paired coordinates I and j, which is an image coordinate, and xy, that is a map coordinate, from many GCPs can be modeled to derive geometric transformation coefficients. These coefficients may be used to geometrically rectify the remote sensor data to a standard datum and map projection. There are several methods to obtain ground control points. If we are taking from a hard copy planimetric maps where GCP coordinates are extracted using simple ruler measurements or a coordinate digitizer. Digital planimetric maps where GCP coordinates are extracted directly from the digital map on the screen. Using Global Positioning System GPS, GCP can be collected in the field with GPS instruments. Here we can see how a ground control point is taken on an image as well as on a map. The common features which are identical on the both map as well as image has been considered as a GCP point. Digital correction of image coordinates involve two steps basically: georeferencing or spatial interpolation. It refers to the process of assigning map coordinates to image data. Another one is geocoding, that is intensity interpolation. Georeferencing with additional resampling of the image so that the pixels are exactly positioned within the terrain coordinate. Order of transformation. After the coordinate transformation, the raster cells may have been oriented differently than the way they were originally in the raster coordinate system. The positions of original grid cells which have to be interpolated in the mapping coordinate system. Different polynomial equations are used to convert source file coordinate into a referencing map coordinates. These are depending upon the distortions in an image, the number of GCPs used and their locations relative to one another. Complex polynomial equations may be required to express the needed transformation. What is the relation of GCPs and order of transformation? It is always advised to use more than minimum number of GCPs or ground control points whenever possible. Although it is possible to get a perfect fit, it is rare. No matter how many GCPs are used, for first through 10th order transformation, the minimum number of GCPs required to perform a transformation is listed in the following table. If it is a first order transformation, minimum GCPs required are 3. If it is second order transformation, minimum GCPs required are 6. Like that. There are different transformation methods. What are these transformation methods? Two-dimensional Cartesian coordinates, that is xy, can be transformed from one coordinate system to another coordinate system using three primary transformation methods, which are conformal, affine, and second-order polynomial transformation methods. Another factor which we should understand regarding root mean square. What is RMS or what is RMS error? The statistical technique of least squares regression is generally used to determine the coefficients for the coordinate transformation equations. If we want to minimize the residual error or root mean square error between the predicted x location and observed original locations, it is calculated as follows. What is geocoding? Georeferencing with additional resampling of the image so that the pixels are exactly positioned with the terrain coordinate system. That particular process we call it as geocoding. Let's see what are those resampling methods for geocoding. The attribute value is to be interpolated for the cells oriented to the new coordinate system, that is called as resampling. There are three common methods of resampling: nearest neighbor, bilinear interpolation, and cubic convolution. The resampling is used to determine the digital values to place in the new pixel locations of the corrected output image. It is a process of fitting one raster grid to the new rectified raster grid. The inputs and output grids do not match exactly. Three common methods of resampling. Nearest neighbor. In this method, the attribute value of the original cell nearest to a cell in the output raster layer is assigned to the corresponding cell. Whereas in a bilinear interpolation, it assigns the value to a cell in the output raster layer by taking weighted average of the surrounding 4 cells in the original grid nearest to it. Whereas cubic convolution, it assigns the value to a cell in the output raster layer by taking weighted average of the surrounding 16 cells in the original grid nearest to it. So operationally, these three methods of resampling are different. Here we can see how these values are assigned. We can see the source grid with GCPs, output grid with GCPs, source grid laid over output grid with GCPs aligned, so the pixel values from the sources are assigned to pixels in the output grid using the different resampling methods which we have explained in the earlier slide. Types of geometric corrections. Two common geometric correction procedures are often used by scientists to make digital remote sensor data of value. One is image to map rectification and image to image registration. The general rule of thumb is to rectify remote sense data to a standard map projection, whereby it may be used in conjunction with other spatial information in a GIS to solve various problems. Image to map rectification, a process by which the geometry of an image is made planimetric with reference to a projected map. It involves the measurement of the image coordinates of the reference cells that is our GCPs, and the corresponding ground coordinates to relate the image with real world. In the below image, we can see the ground control points are taken in a common locations both in a map as well as on a satellite imagery. Here again we can see the common points located on a satellite imagery and the corresponding topo sheet of an area. Image to image registration. In image to image registration, it is a method of georeferencing a raster layer with the help of another raster layer, which is already georeferenced by the process of image to map rectification, which we have seen in the earlier slide. Control points are selected from the two raster layers, that is, from two image layers. The coordinate transformations and resampling is then done in the similar manner as it is done for an image to map rectification. The image used as a reference with non-projection and coordinate is called as a master image, and the image to be registered is called as subject image. It is important that the reference map or image is rendered in a standard map projection and coordinate system. Let us discuss about radiometric correction. As a pre-processing, radiometric corrections are applied as cosmetic corrections as well as atmospheric. Radiometric correction of remotely sensed data normally involves the process of digital image to improve the fidelity of the brightness value magnitudes. It reduces the influence of errors or inconsistencies in image brightness value that may limit one's ability to interpret or qualitatively process and analyze digital remote sensing data. Cosmetic corrections. Line dropout correction. Line dropout is one of the radiometric errors which has to be corrected. The first step in the restoration process is to calculate the average DN value per scan line for the entire scene. And the next step is to replace the defective line. For each pixel in a defective line, an average DN is calculated using DNs of the corresponding pixel in the preceding and succeeding scan lines. The average DN is then substituted for the defective pixel. In this picture, we can see a particular line where the zero values are given, where the DN values are null values, and in the image we can see a line dropout. These corrections are done as we explained by taking the average DN values in the preceding and succeeding scan lines and substituting these null values. Line banding correction. Line banding is other radiometric error. If one detector is no longer producing data readings consistent with the other detectors in a system, definitely its histogram will be different from the other. You can see in the picture the histogram of detector 1, 2, 3, 4. In that detector 4, their DN histogram is not matching with the other 3. The DNs produced by all the detectors are altered so that their histograms are then made to match the average one. When this procedure is completed, the imbalance between the detectors is eliminated and the image is said to have been de-striped. Atmospheric attenuation. Solar radiation, when it interacts with Earth's atmosphere, it is selectively scattered and absorbed. The sum of these two forms of energy loss is called as atmospheric attenuation. How this atmospheric attenuation affects the magnitude of radiance leaving ground is attenuated by atmospheric absorption, and the directional properties are altered due to scattering. Other sources of errors are due to the varying illumination geometry dependent on a sun azimuth and elevation angle with ground terrain. This will be affected or generated as an radiometric error in our. So we are performing various atmospheric corrections on our data. Absolute atmospheric correction. The general goal of absolute radiometric correction is to turn the digital brightness value or DN into a scaled surface reflectance value. So as the data we are receiving, we can convert the DN into radiance and into reflectance. Relative atmospheric correction. It is also called as image normalization. This procedure uses a standard image to normalize the other. It temporarily adjusts the images. The statistical or empirical based atmospheric correction models provide good estimates of the surface reflectance by this. Here we can see an image before correction and after correction. The influence of atmospheric attenuations are corrected by applying various radiometric corrections. Here we can see haze reduction. The presence of haziness in a satellite imagery is removed by applying the atmospheric correction methods. Through this, which we can generate or make our imagery more visible and interpretable. So, through this lecture, you have understood about various errors in a remote sensing data and how we can correct those errors using various methods. Thank you for watching. This is the end of the current session, and the next session is on introduction to image processing technique.